Welcome to the world of digital electronics, where logic meets innovation to power modern technology. This presentation, including all content, visuals, and materials, is the exclusive property of Semiconductor Private Limited. All rights are reserved. Unauthorized copying, reproduction, distribution, or disclosure of any part of this material in any form or by any means is strictly prohibited without prior written permission from Semiconductor Private Limited. The company name, logo, and all related marks are trademarks or registered trademarks of Semiconductor Private Limited. This document and its contents are confidential and intended solely for authorized individuals. Any unauthorized use, review, or sharing of this information may result in legal action. Copyright Semiconductor Private Limited. All rights reserved. Welcome to the Digital Electronics Learning Session. Get ready to explore how zeros and ones form the backbone of every modern device, from smartphones and computers to embedded systems and processors. In this course, we'll uncover how digital circuits, logic gates, and binary systems power the technology that drives our world. Analog systems deal with continuous signals, helping us understand real-world phenomena, which is essential before learning digital systems that work with discrete signals. An analog system processes continuous time signals that can take any value at any instant. Unlike digital systems, which handle discrete levels, analog systems deal with smooth variations like voltage, current, or sound waves. Examples include amplifiers, filters, and FM radios. These systems are widely used in sensors and communication circuits, where real-world data must be captured and processed accurately. In simple terms, analog systems form the foundation for converting physical signals into meaningful electrical information. In contrast to analog, a digital system works with signals that are discrete in nature. These signals are represented as binary values, either a 0 or a 1. Instead of smooth variation like analog signals, they jump between these two definite states. A simple way to understand a digital system is to imagine a light switch. It is either on or off. There is no middle brightness in a pure switch. This is exactly how a digital system interprets information. Two distinct states with no in-between levels. If the switch is turned on and off repeatedly over time, the signal pattern we get forms a square wave, which is a typical representation of digital signals in electronics. Digital systems process information step by step in binary form. These steps are called bits. A combination of bits allows us to represent numbers, characters, images, and complex operations that computers perform. Let's see an example.
Welcome to the world of digital systems, where everything you see, hear, and interact with is powered by a simple yet profound language, binary code.
An ATM machine is a perfect example of a digital system. When you insert your ATM card or enter your PIN, the information is captured as digital input. The ATM's internal computer processes this information using binary logic and verifies it with the bank server. All the stored user data, like account number, balance, and PIN, is stored in binary format. If the PIN matches, the system moves to the next state. If not, it denies access. This is an example of a discrete, step-by-step digital decision. Finally, the ATM displays the result digitally on the screen and dispenses cash based on binary-controlled actuators. Let's see an example.
Welcome. Please insert your card to begin. Select your transaction type. Processing your request. Please take your cash.
In reality, analog and digital systems often work together. The world around us is analog. The sound we hear, the light we see, the temperature we feel. To process this data digitally, it must first be converted into binary form using an analog-to-digital converter, ADC. Once in digital form, computers, smartphones, or other digital systems can process, store, and transmit the data efficiently. After processing, the data is often converted back into analog using a digital-to-analog converter, DAC, so that humans can perceive it, like listening to music or viewing an image on a screen. Examples of this combination include audio players, cameras, medical monitoring devices, and smartphones. This synergy allows us to leverage the advantages of both analog and digital systems. Let's enjoy a break. Number systems are exciting methods of representing numbers using a wonderful set of digits or symbols. They beautifully define how we write, store, and compute values. In the fascinating world of electronics and digital systems, number systems play a fantastic role because computers can only understand delightful forms like binary, octal, or hexadecimal. Let's look at what kind of numbers we use in our daily lives. This system is known as decimal. The decimal numbers range from infinite to infinite. However, the fundamental decimal numbers are from 0 to 9. It has a base of 10. Let's understand how the decimal number system, called base 10, works. How many digits do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We have a total of 10 numbers. Any decimal number can be formed from the basic numbers 0 to 9, so it is called base 10. Let us take the decimal number 42345 one narrowed. The base of this number is 10, which means every digit in this number is multiplied by a power of 10 according to its position. In step 1, we break the number based on place value. 4345 in area equals 4 times 1000 plus 3 times 100 plus 410 plus 5 and 1. This shows the expanded value using normal place values, thousands, hundreds, tens, and ones. In step 2, the same expansion is shown using powers of 10. 4345 1 equals 4 times 10 ku plus 3 I 10 squared plus 4 times 10 non plus 5 times. Here you can see that each position from left to right is associated with a different power of 10. Tens go for the thousands, place 10 squared for the hundreds, place 10 non for the tens, place 10 secs for the units place. This proves that any decimal number can be represented using its base 10 and the coefficient values of each digit. Please notice the general equation. This method of representation is called positional or weighted representation because the position of a digit determines its weight. Binary numbers use only 2 digits, 0 and 1. That is why their base is 2. Each binary digit is called a bit, and every bit represents a power of 2 depending on its position. In binary, 0 when 0 use is written as 0 2, 1 when you 1 2, 2 when use is written as 10 2, 3 is written as 11 2. This means that binary numbers count in powers of 2 instead of powers of 10, like in the decimal system. So while decimal moves 8, 9, 10, binary moves 1, 10 because it cannot use the digit 2. Octal numbers use 8 digits, 0, 1, 2, 3, 4, 5, 6, and 7. That is why the base of the octal system is 8. Octal works in the same way as decimal and binary, but instead of powers of 10 or powers of 2, it uses powers of 8. It is often used in digital systems as a short form of binary because every one octal digit corresponds to exactly 3 binary bits. For example, 8002 equals 10 3. Here's what happens. The decimal number 8 is written as 1002 in binary. Now, if we group binary digits in sets of 3 from right, 1000, 10,000, 10 trash spide. So the octal representation becomes 10. This shows how octal provides a compressed representation of binary numbers, making large binary values easier to read and handle in digital electronics. Just like decimal uses 10 digits and binary uses 2 digits, hexadecimal uses 16 different symbols. These symbols include the digits 0 to 9, and then we continue using letters A to F to represent values from 10 to 15. Hexadecimal is very commonly used in digital electronics because it provides a compact way to represent large binary numbers. For every 4 binary bits, we get exactly 1 hexadecimal digit, which makes conversions very easy. For example, the decimal number 12 in binary is 1100. If we group 4 binary bits, 1100 directly becomes C in hexadecimal. So 12 base 10 equals 1100 base 2, C base 16. In hardware design, memory addresses, machine instructions, and register values are almost always written in hexadecimal because they are shorter and easier to read than long binary strings. A radix, or base, simply tells us how many unique symbols a number system uses. If a number system has base r, then it can use exactly r different digits, starting from 0 up to r minus 1. For example, in a 3-radix system, the available digits are 0, 1, and 2. That's 3 unique symbols. Similarly, a 4-radix system uses digits from 0 to 3, and a 6-radix system uses digits from 0 to 5. So the general rule is, a number system with base r always contains digits from 0 to r minus 1. This concept forms the foundation for understanding binary base 2, octal base 8, decimal base 10, and hexadecimal base 16 number systems. There are multiple number systems used in digital electronics, each defined by how many unique digits it contains. The decimal system is the one we use in everyday life, and it has 10 symbols from 0 to 9, which is why its base is 10. In computers and electronics, however, everything runs on binary, which has only 2 digits, 0 and 1. These are directly understood by digital hardware through low and high voltage levels. To make binary easier to read, especially when numbers become large, we also use octal and hexadecimal. Octal uses 8 digits, 0 to 7, and helps shorten long binary values by grouping 3 bits. Hexadecimal uses 16 symbols, 0 to 9 and A to F, and is very convenient for memory and processor level representation because every 4 bits convert into exactly 1 hex digit. So, decimal is used for human-friendly calculations, binary is used by hardware internally, and octal and hexadecimal act as compact notations that make binary representations simpler to read and work with. Before we move into more complex number systems, let's understand how to convert from one base to another. We'll begin with the most common conversion used in digital electronics, converting a decimal number into binary. Let's take the decimal number 25 as our example and convert it step by step into binary. To do this, we repeatedly divide the number by 2 and record the remainder each time. First, 25 divided by 2 gives 12 as the quotient and 1 as the remainder. Then we divide the quotient 12 by 2 to get 6, remainder 0. Continuing the same process, 6 divided by 2 gives 3, remainder 0. 3 divided by 2 gives 1, remainder 1. And finally, 1 divided by 2 gives 0, remainder 1. Once the quotient becomes 0, we stop dividing. Now, to get the binary result, we read the remainders from bottom to top, or in reverse order, so the sequence becomes 11001, which means that decimal 25 is equal to binary 11001. This method is called successive division by 2, and it forms the foundation for decimal to binary conversion. Review our 25 decimal conversion to binary here, before moving to the next. When converting a binary number into decimal, we apply positional weights based on powers of 2. Starting from the rightmost bit, we use 202, 2020, then 212, 2121, and so on, moving left. For the binary number 11011, the leftmost 1 is multiplied by 242, 2424. The next one by 232, 232. The middle 0 by 222, 222. Then the next one by 212, 2121. And the final one by 202, 2020. Adding all the weighted values together gives 16 plus 8 plus 0 plus 2 plus 1 equals 27. Therefore, 110112 in binary is 27 in decimal. To convert a decimal number into octal, we use the same successive division idea you used for decimal binary, but instead of dividing by 2, we divide by 8. Each remainder becomes 1 octal digit. Let's convert 125 base 10 into octal. Step 1. 125 divided by 8 equals 15, remainder 5. Write down remainder 5. Step 2. Take the quotient 15. 15 divided by 8 equals 1, remainder 7. Write down remainder 7 above the previous remainder. Step 3. Take the quotient 1. 1 divided by 8 equals 0, remainder 1. Write down remainder 1 above the previous remainders and stop because quotient is now 0. Now read the remainders from bottom to top. Last remainder obtained, first remainder, 1, 7, 5. So 125/10 equals 175/8. That's the whole method. Divide by the base you want. 2 for binary, 8 for octal, 16 for hex. Collect remainders, then read them in reverse. Now, let's dive into the process of converting an octal number into decimal using positional weights. We'll start with the number 546 in base 8. Octal means base 8, so each digit is multiplied by a power of 8 according to its position, starting from the right, with 8 raised to the power of 0, then 8 raised to the power of 1, then 8 raised to the power of 2, and so on. In octal number 546, the rightmost digit 6 is in the 8 squared place, so it becomes 6 times 1 equals 6. The next digit 4 is in the 8 squared 1 place, thus it becomes 4 times 8 equals 32. The leftmost digit 5 is in the 8 squared 2 place, therefore it becomes 5 times 64 equals 320. Now we add all three contributions. 320 plus 32 plus 6 equals 358. So the octal number 546 base 8 is equal to 358 in decimal, or 546 equals 358/10. This method is very similar to binary to decimal conversion. The only difference is, instead of powers of 2, we use powers of 8. Let's now convert the decimal number 2347 into hexadecimal form. Since hexadecimal uses base 16, we divide the number repeatedly by 16. 2347 divided by 16 gives a quotient of 146 and a remainder of 11, which is B in hex. Next, 146 divided by 16 gives a quotient of 9 and a remainder of 2. Finally, 9 divided by 16 gives a quotient of 0 and a remainder of 9. Now, write all remainders from bottom to top. That's 9 to B. Therefore, the hexadecimal representation of decimal 2347 is 9 to B. Now, let's convert the hexadecimal number 4e2a into decimal. Just like decimal numbers, which use powers of 10, hexadecimal numbers indeed use powers of 16 because their base is 16. So each digit in the number gets multiplied by 16, raised to the power of its position, starting from right to left. Let's separate the digits. A is in the rightmost position, and in hex, A means 10. Before that, we have 2. Then we have E, which is equal to 14 in decimal. And finally, we have 4. Now we assign the positional weights. The rightmost digit, A, is multiplied by 16 to the power of I. 2 is multiplied by 16 to the power of 6. A is multiplied by 16 to the power of 4. Now let's calculate step by step. A 10 times 16 equals 10 times 1 is 10. 2 times 16 equals 2 times 16 equals 32. E 14 times 16 to the power of 256 equals 3584. 4 equals 4 times 16 cubed equals 4 times 4096 equals 16,384. Now we add all these values together. 16,384 plus 3,584 plus 10 equals 2,010. So the final result is 4e2a in hexadecimal is equal to 2,010 in decimal. This is how we convert a hexadecimal number to decimal, using positional weights of 16. Here, we can see how the same value is represented in 4 different number systems. The first column is decimal, our everyday number system with base 10. The second column is binary, used in digital circuits and computers, and works on base 2. Next is Octal, a base 8 system that groups binary digits in sets of 3. And finally, Hexadecimal, a base 16 system that is widely used in programming and memory addressing. Notice that from decimal 0 to 9, the symbols are the same in all systems, but after 9, hexadecimal uses letters A to F. This table gives a clear mapping between different number systems. Here are a list of example problems. Solve yours yourself and discuss in the comment section. 4 solutions. Welcome to the topic of weighted number systems. In a weighted number system, every digit in a number carries a value based on its position. This positional weight determines the overall value of the number. Familiar systems such as decimal, binary, octal, and hexadecimal are all weighted systems because each digit contributes a weight based on a power of its base. If you remember, we have used the same positional weighted approach while converting binary, octal, hexadecimal values into decimal numbers. We can see how each number system is defined by its base and its corresponding positional weights. In the decimal system, the base is 10, so the weights are powers of 10, such as 1, 10, 100, and 1000. In binary, the base is 2, so the weights are powers of 2, like 1, 2, 4, 8, and 16. Similarly, octal works with base 8 and uses weights like 1, 8, 64, and so on. And hexadecimal uses base 16 with weights such as 1, 16, 256, and 4096. Each example shows how a number is expanded using its weights. This helps us understand that the value of a digit does not depend only on the digit itself, but also on the position where it appears. A non-weighted number system is one in which the digits do not have positional weights. That means the value of a digit does not change based on its position, unlike decimal or binary. These systems are typically used for error detection, digital communication, and data encoding, rather than arithmetic operations. Examples of non-weighted codes. These include gray code, oh yes, which changes only one bit at a time. This technique reduces errors. Then we have XS3, used primarily for error detection in decimal systems. How fascinating! BCD, or binary coded decimal, represents each decimal digit separately in binary. Isn't that interesting? And let's not forget ASCII, which is used for representing characters and text in computers. These number systems, you see, focus more on reliable representation and communication, rather than mathematical value. Gray code, also known as reflected binary code, is a special type of binary numbering system where only one bit changes between consecutive values. Unlike normal binary, where multiple bits may change at once, gray code changes just a single bit, which makes it a non-weighted code. This property helps minimize errors caused by sudden bit transitions, especially in mechanical or digital sensors and rotary encoders. That's why gray code is widely used in encoders, position sensors, communication systems, and error reduction applications in digital electronics. To convert from binary to gray code, we follow a simple rule. The MSB, or leftmost bit, of the gray code is exactly the same as the MSB of the binary number. For all the remaining bits, each gray code bit is generated by XORing a binary bit with the previous binary bit, meaning the bit immediately to its left. In formula form, GI equals BI into BI plus 1 for all bits except the MSB. Let's take an example with the binary number 1011. The MSB is 1. So, the first gray bit is also 1. Next, we take the second binary bit, 0, and XOR it with the previous bit, which is 1. Therefore, 1 XOR 0 equals 1. We take 1 and XOR with the previous bit, 0, giving us 1. Finally, we XOR the last one with the previous one, yielding 0. Thus, the binary number 1011 becomes 1110 in gray code. Therefore, 1011 binary equals 1110 gray code. Let's learn how to convert a gray code number into its equivalent binary number in a simple and easy way. Step 1. Keep the first bit the same. The first bit of the binary number is always the same as the first bit of the gray code. Step 2. XOR with the previous binary bit. For all the remaining bits, we take the previous binary bit and perform an XOR with the current gray code bit. XOR means if the two bits are the same, 0. If they are different, 1. Example, let's convert gray code 1101 to binary. First bit, same as gray code, equals 1. Binary so far, 1 up up. Second bit, previous binary bit 1, XOR gray bit 1 equals 0. Binary 10 up up. Third bit, previous binary bit 0, XOR gray bit 0 equals 0. Binary 100 up. Fourth bit, previous binary bit 0, XOR gray bit 1 equals 1. Binary 1100. So gray code 1101 converts to binary 1100. XS3, or XS3, is a non-weighted binary-coded decimal code. It is created by adding 3 to each decimal digit, and then converting the result into a 4-bit binary number. Why is it called XS3? Because each decimal digit is represented in binary with an excess of 3. The formula is simple. XS3 code equals decimal digit plus 3. Let's see an example. Suppose we want to encode the decimal number 7 in XS3. First, we add 3 to 7. That gives us 10 in decimal. Next, we convert 10 into a 4-bit binary number, which is 1010. So in XS3, decimal 7, which is 0111 in binary, becomes 1010 in XS3. And that's how XS3 coding works. BCD stands for binary coded decimal. It's a method of representing decimal numbers from 0 to 9 in binary form. In BCD, each decimal digit is converted separately into its 4-bit binary equivalent. Let's look at some features of BCD. Each decimal digit is represented using 4 bits. It is easy to interface with decimal displays, such as 7-segment displays. However, it wastes some bits because combinations from 1010 to 1111 are unused. BCD is also less efficient for arithmetic operations compared to pure binary representation. That's the essence of binary-coded decimal, a simple way to handle decimal numbers in digital systems. Now let's take a look at the BCD table, shall we? It illustrates precisely how each decimal digit finds its representation in binary. Decimal 0 is represented as 000 in BCD. Decimal 1 corresponds to 0001. Decimal 2 is denoted as 0010. Decimal 3 appears as 0011. Decimal 4 translates to 0100. Decimal 5 is shown as 0101. Decimal 6 captures 0110. Decimal 7 showcases 0111. Decimal 8 manifests as 1000. Decimal 9 concludes with 1000. Notice that each decimal digit is represented using exactly 4 bits, and the combinations from 1010 to 1111 are not used in standard BCD. This table is very useful when interfacing with digital displays or microcontrollers, as it provides a direct mapping from decimal to binary digits. Now let's see an example. Suppose we want to represent decimal 59 in BCD. First, break it into decimal digits. 59 is 5 and 9. Next, convert each digit into 4-bit binary. 5 becomes 0101, and 9 becomes 1001. So in BCD, 59 is represented as 0101, 1001. Let's compare BCD and pure binary. First, consider the table. In BCD, each decimal digit from 0 to 9 is represented using 4 bits. In binary, digits are just 0 or 1, without any limit on the number of bits. BCD is less efficient because it uses extra bits. However, pure binary is highly efficient. BCD is commonly used in digital displays and calculators, whereas binary is utilized in computers and processors. In this session on ASCII, the American Standard Code for Information Interchange, ASCII is a character encoding standard that assigns numeric values to letters, digits, symbols, and control characters. Simply put, it allows computers to represent and exchange text in a way that both humans and machines can understand. For example, the capital letter A is represented by the number 65 in ASCII, while lowercase a is 97. The digit 0 has a code of 48, and the space character is 32. In total, standard ASCII defines 128 characters, ranging from 0 to 127, covering all the letters, numbers, basic punctuation, and some control codes like carriage return or line feed. ASCII. It is extremely important. Why? Because it ensures consistent text communication between devices, applications, and networks, whether you are writing code, sending an email, or even storing text. ASCII guarantees that the characters are correctly interpreted across systems. In summary, ASCII bridges human-readable text and machine-readable numbers. Understanding it is fundamental for programming, digital electronics, and networking. Later, we will also look into extended ASCII, which allows even more characters, including symbols and foreign language letters. That's your complete introduction to ASCII, the foundation of text representation in computers. Here are a list of example problems. Solve yours yourself and discuss in the comment section. 4 solutions. Let's talk about unsigned numbers. Unsigned numbers can only represent positive numbers. Yes, including 0. In unsigned numbers, no bit is reserved for a sign. That means all bits are exclusively used to represent the magnitude of the number. If you have n bits, the range of values you can represent is from 0 to 2 to the power of n minus 1. For example, let's examine a 4-bit unsigned number. 000 represents 0. 001 represents 1. 00 represents 2. And so on, up to 1111, which represents 15. So, with 4 bits, you can represent numbers from 0 to 15. Remember, no negative numbers can be represented in unsigned numbers because there's no sign bit. In digital electronics, signed numbers help us handle values above and below 0. The MSB is reserved as the sign bit. 0 indicates a positive number. For example, 0101 represents +5. 1 indicates a negative number. For example, 1101 represents -5. There are 3 methods to represent signed numbers. Sign magnitude, 1's complement, and 2's complement, which is the most widely used method. We will discuss each method in the next slides. Now, Let's explain what's happening here. In the first example, 0001, the sign bit is 0, so it's positive, and the magnitude 001 equals 1, that's plus 1. In 1001, the sign bit is 1, meaning it's negative with the same magnitude 001, giving us minus 1. Similarly, 0010 represents plus 2, while 1010 represents minus 2. Finally, 0111 equals plus 7, and 1111 equals minus 7. So, the sign bit controls the sign, and the remaining bits define the value. Although sign magnitude is simple to read and understand, it's not very efficient for performing arithmetic operations like addition or subtraction, which is why other methods, such as 1's complement and 2's complement, are more commonly used. Now, let's learn how to find the 1's complement of a binary number. The 1's complement method is another way to represent negative numbers in binary form. Here's the rule. To find the 1's complement of a number, write the positive number in binary. Then, flip every bit, change 0 to 1 and 1 to 0. Now, let's explain step by step. For plus 3, the binary form is 0011. To get minus 3, invert each bit. Zeros become 1's, and 1's become 0's, giving 1100. Likewise, plus 5 in binary is 0101. Inverting all bits results in 1010, which denotes negative 5 in 1's complement form. Therefore, keep in mind, in 1's complement, the positive number remains unchanged, but for a negative number, we invert all the bits of its positive counterpart. Now let's explore the 2's complement representation, a widely used method to represent signed binary numbers. In this method, similar to 1's complement, the most significant bit, MSB, indicates the sign. 0 means the number is positive. 1 means the number is negative. Here are the steps to find the 2's complement of a number. Write the number in binary. Take the 1's complement by inverting all bits. Add 1 to the least significant bit of the 1's complement. Let's take examples. With a 4-bit number, 5, it's a 2's compliant number. Negative 5, the binary form of 5 is 0101. The 1's complement of 5 is 1010. The 2's complement equals the 1's complement plus 1, which results in 1011, positive number, plus 5, 0101. Negative number in 1's complement, minus 5, 1010. Negative number in 2's complement, minus 5, equals 1011. The range of n-bit 2's complement numbers is from minus 2 to the n-1 to 2 to the n-1 minus 1. For example, an 8-bit number can range from minus 128 to plus 127. Advantages of 2's complement. Simplifies addition and subtraction operations. Eliminates the need for end-around carry, which is required in 1's complement. Provides a single representation for 0. Key property. Addition and subtraction work directly, without needing separate subtraction circuits, making arithmetic much simpler in digital systems, etc. Computers represent real numbers using a system called floating point representation, which allows us to store very large or very small numbers efficiently. A real number in this system has two main parts. The mantissa, also called the significand, which holds the significant digits of the number. The exponent, which scales the number by a power of the base. In computers, this is usually base 2. The general form can be written as number equals mantissa times base to the exponent. For example, the decimal number 5.75 is represented in binary as 101.11. Normalized, it becomes 1.0111 times 2 to the power. Key points to remember. Floating point numbers allow us to represent very large and very small numbers. They can store fractional values. Unlike integers, floating point numbers use a fixed number of bits for the sign, exponent, and mantissa. The widely used standard is IEEE 754, which defines single precision 32-bit and double precision 64-bit formats. Advantages: efficient storage and computation of fractional and exponential numbers. Compact representation for a wide range of values. Limitations: finite precision can indeed lead to round-off errors. Some decimal fractions, unfortunately, cannot be represented exactly in binary. Understanding floating point representation is essential because it allows computers to handle real-world calculations accurately and efficiently. Let's convert 8.625 into binary form. Step 1. Separate the number. 8 is the integer part, and 0.625 is the fractional part. Step 2. Convert the integer part. Divide 8 by 2 repeatedly and note remainders. 8 divided by 2, 0. 4 divided by 2, 0. 2 divided by 2, 0. 1 divided by 2, 1. Read from bottom to top. 1, 0, 0. Step 3. Convert the fractional part. Multiply 0.625 by 2 repeatedly. 0.625 times 2 equals 1.25. Take 1. 0.25 times 2 equals 0.5. Take 0. 0.5 times 2 equals 1.0. Take 1. So fractional part equals 0.101. Step 4. Combine both parts. 8.625 is 1000.10 first. That's the binary form of 8.625. Integer part 1000, fractional part 0.101.